All right, Mr. Claxon's algebra students, we are here today because, well, we want to answer the following essential questions that you see right now. What does a line represent when it's graphed on an XY plane? Essentially, what we're asking ourselves is, what is a line? Algebraically speaking, of course. You know, you started out, and maybe you started out in kindergarten or first grade just drawing lines. And we drew the type of lines that weren't exactly straight lines. They were just a long, narrow mark on a surface. That's what Merriam-Webster calls it. And that's the basic definition of a line. You can make a line just by making a long mark. And that long mark can keep going. I just made a curved line. You can see the red curved line and the blue curved line. And then we start to graduate our thinking as a line between 2 points. The shortest distance between 2 points we all know is a straight line, and we start to come to understand lines as something, okay, we're going to take 2 points, you see the blue points there, and we're going to draw something straight between them by using a straight edge, and that would be a straight line. And then in our academic careers we come across, well, a linear equation, right? And that creates a line on an XY plane or a Cartesian plane. So with the linear equation, we now have an equation whose graph is a straight line. So you can see the blue line right here that I just selected. It's a solution set that satisfies all possible XY values that can be plotted to the line. So if you were just looking for the answer for the first part of our essential question that we started with, you might go back and you might be able to answer that now. We're going to keep moving on, though. We also start to refer to these linear equations as functions as well. So what does that mean? Well, it starts to get just a little more complicated because you see, for example, let's take this linear equation. Let's take this linear equation that I have right up here in black. This linear equation represents all of the solution sets that make up negative x plus 2y equals 4. And there are many different ways to even write this line. I could also rewrite this, and it's going to be the same line, mind you, as negative 2x plus 4y equals 8. And you probably noticed that I just multiplied every value by 2. You could even multiply every value by 1.5 if you wanted to. So you could say negative 1.5 x plus, and then we're going to take 2 and multiply it times 1.5. So you might say 3y if you were thinking along with me. And then we got 4 multiplied by 1.5. Now I like to refer to fractions whenever I do that, and you might be doing it right now as well. Remember, we're multiplying by 1.5. 12 over 2 is just 6. 4 times 3 is 12. And basically, I did 4 over 1 times 3 over 2 is what I did there. So, looking at this, what we've got here is we've got the same line. All of these represent this blue line down here. We're going to go back to that. Well, it's not the easiest way, but it's a linear equation. We call this standard form. If you look down here, I've taken x values, and I've ran the x values all the way from negative 4 to 6. And you can see this first x value that I chose here was negative 4. Now, in order to find the y value, I did have to plug it in. I had to plug it into this equation. I plugged it in for x, negative 4, ends up being positive 4. Subtract that from each side, and you get 2y equals 0. Divide each side by 2, and we get 0. So when x is negative 4, y is 0. That is one of the solutions to this line. So you might also call that a solution, right? It's a solution. But we have many solutions for this one line, right? That's a solution. And then we have another solution. And you've probably noticed that I could go all the way down here and draw arrows or curved lines to those. And you see the corresponding point over here. We see the point -4, 0, -4, 0. You see right there. And then you might even see a pattern here. Well, -3, 0.5, so -3 on this xy plane. And up about a half. If this is 1 over here, then I know up about a half is about that much. And then -2, at -2, up 1, okay. So you're seeing that point. And then you might be saying to yourself, wait, I see that it's going up a half each time. Or really, for every 1 that it goes up, we're going right 2. Up 1, right 2, up 1, right 2, and up 1, right 2. Now you can see that we could, we really wouldn't even have to calculate after we did plot this line and see the pattern. You might be able to just come down here and say, well, this is pretty easy, Mr. Claxon. I know that in the next one, we're going to have 2. I'm going to skip 1 there, and then I know it's going up 2 again. Or up 1 again, Mr. Claxon. Up 1 again. And then, skip 1. All right. And skip 1 down here to 6, 5. And, if we would solve the equation every time, for example, add 6, then divide by 2, we are going to get the y value. And you know that really it goes up a half, right 1. Up 1/2, right 1. So I know that in between here I'd get 2.5. In between x equals 2 and x equals 4, right? We have x equals 3, so that's going to be 3.5. Now, I know that you get the point here, pun intended. Always make sure we bring those decimals down. Yeah, those decimals need to live on the bottom. Otherwise, that looks like 4 times 5. So we see all these points, and we know that even in between those points, if I wanted to enter in a crazy point, which we're going to do here in a little bit, like -3.9, -3.9, I have a y value that exists because I have this equation, and you might have already figured out that the slope of this line is 1/2, and we have a special point down here, this special point, which I'm going to go ahead and circle, which you might know. You might be thinking, oh yeah, I already identified that as the Y-intercept. So if you look right here, we've got this line graphed again. You might notice this as slope-intercept form with a Y-intercept of 2 and a slope of up 1, right 2, which is just 1/2. Well, we know that this relationship works for any possible x value that I can plug in. So, if we were to plug this into a calculator and graph it, and we want to trace our graph now, what I say? I said, well, -3.9 is a crazy value. Let's get sick with it. Let's get a little crazy. Does that return a value? Yeah. 5/100. It returns 5/100. What if I wanted something like -3.8? What would I get? Oh, that's 1/10. Well, what if I want to say something like -3.0006? Would that return a value? Absolutely. The value that returns is 4,997 10,000ths. Okay, so you can see that, and we could I could throw something that's going to be off this graph here, like 200. It probably will not return a value. It's going to tell me, oh my goodness, Mr. Collection, you entered in something that's too big. I could go to the table if I wanted to do that. I could go to my table. Oh, I should probably say quit first, right? Quit. And I could go to my table. First, I got to make sure my table's set. Oh, my table needs to be set on ask. I want it to ask me. So I could go to my table, and I could enter in something like 200, for that matter, and it would give me an output of 102. So I hope that you now understand really what a line is and what we're trying to graph whenever we graph a line. I thank you for watching, and I hope you learned something today.